Otherwise, I will introduce our next and our final speaker of the day, Kyoung Hyun Lee. He's here to talk to us about bifurcation-based machine learning of dynamical systems. Take it away whenever you're ready, Kyung.
Okay, hello everyone. My name is Gyung and I'm a PhD student at University of Bristol. And my supervisors are David Barton and Ludovic Ranson. And today I will talk about bifurcation-based machine learning of dynamical system, which is example of applying SciML packages for system with bifurcations in nonlinear dynamical systems. I will introduce some examples from experimental bifurcation analysis to using experimental bifurcation analysis to build the dynamical system models. I'll first show you some example of parameter-dependent systems that undergoes bifurcations. Oh, sorry. Yeah, I have problem with. I think I have problem with videos in this slide. Yeah.
Oh, I see. If did you upload a PDF or a Google slide up here?
I uploaded my slide here.
I see.
Oh, yeah, it's actually it was shown in my colleague's slide, Sandor's slide.
You
It was
can send links to it, and I can just send it to the Discord if that's easy. But you should continue with your talk.
oh yeah, I'll just continue with it. It's self-excited system example of self-excited systems, like in airplanes at certain speeds. There could be some limit cycle oscillations on airplane wings, and it can end up of disasters. So usually researchers doesn't want those kind of problems, and these are the first example that I wanted to show was the it's called aeroelastic flutter, and the wing flaps at certain wind speeds. And another example that I wanted to show on this second video was a wheel shimmy, which at certain speed of the vehicle with wheels, it can lose like its controllability or maneuvering ability. So it's called as limit cycle oscillations and self-excited systems. And this type of dynamical system without an external excitation is often called a self-excited system. And it is quite challenging to make a model that can predict this phenomena accurately. And I'll show you some example that if we use SciML packages, then we can model these systems quite interestingly. And self-excited systems are typically modeled with ODEs with Hopf bifurcation. And we can understand Hopf bifurcation geometrically from this figure here. And at certain parameter value of mu, we call this control parameter. And there can be change of stability, changing of an equilibrium, and the branch of limit cycle oscillation is generated at this equilibrium. And self-excited vibrations that we observe that are shown in the previous slides are some stable limit cycles somewhere over in the upper branch over here. And there are some interesting characteristics of systems with bifurcations that we can use in modeling, which is like existence of an invariant manifold, which I will explain from the next slide. And invariant manifolds are submanifold of state space that are preserved under the flow. And this is a very nice figure explaining the invariant manifold of the flows flows starting in this manifold stays in this manifold. And dynamics on this manifold is called reduced dynamics. And many reduced order modeling starts with finding this manifold from the full scale ODEs. And system with Hopf bifurcation has a center manifold. And for example, damped mechanical systems has some invariant manifold as well. And in this case, and we can use the existence of the invariant manifold and the dimension of the invariant manifold as the domain knowledge of the modeling. And this is a general framework of training parameter-dependent ODE models using machine learning. And first, we model the parameter-dependent vector field using scientific models or universal approximators like neural networks, or we can use hybrid models. And we need to also model the observations. For example, we can model this as a just simple projection map or also universal approximators. And after we make a model structure, then we have to transform the parameter identification problem to an optimization problem using data fitting criteria such as mean square error. And I'll explain from the next slide how we infuse the domain knowledge of the invariant manifold and the bifurcation to our machine learning problems. Yes. So basically, I do experiment for system with bifurcations, which is called experimental bifurcation analysis. This is the bifurcation diagram measured from a flutter rig experiment, which is a typical subcritical Hopf bifurcation measurement. These red circles are the measured unstable periodic solutions, which are stabilized using feedback controllers. And these blue circles are the measured stable limit cycle oscillations. So if we draw this bifurcation diagram, then we can plot this like this typical subcritical Hopf bifurcation diagram. And this, we know the bifurcation structure of this measured system, which is a reduced dynamic on the invariant manifold. And the interesting thing of nonlinear dynamical systems are we can use coordinate transformations to transform this dynamical system to a topologically equivalent dynamic systems. And we usually use these coordinate transformations to derive some simple type of ordinary differential equations, which is called normal forms. And these are the simplest usually a polynomial type of equations that reproduces this dynamics in a simplest form. And we can use those kind of differential equations as our basis model. And I'll show you how we can train this system using the normal form. So I'm sorry about the this equations errors. I don't know what happened, but anyway, I'll just go on. The equation I have used to reproduce the dynamics shown in the last slide is using the subcritical Hopf normal form, but I added quintic terms to reproduce the set load bifurcations to to make stable limit cycle oscillations on the upper branch. So this is the basis model I used to make a topologically equivalent dynamic system. And the advantage of using normal form-like equations is that the shape of the trajectory of the LCOs of this system on the normal form coordinates are LCOs, just very simple LCOs with a circle trajectory. And if we transform this to a polar coordinates, and it shows that the amplitude of the normal forms are just simple fixed points, and we can decouple the speed of the oscillations with the amplitude equations. And using this basis model, we can design the bifurcation diagram very easily using these are model parameters A2 to design the bifurcation diagram, and this mu zero is the Hopf bifurcation point, and this large omega is to model the speed of the oscillation, and I use neural network in my modeling case. And this is the summary of training the observable, which is basically a coordinate transformation between the invariant manifold, which is a center manifold in this case, between the invariant manifold and the measured trajectory. So basically, this observable, which is a neural network, it's a combination of linear transformation and the neural network transforms the circle, which is the trajectory of the normal form, and this two measured some complicated closed form shapes. And so in order to match this transformed trajectory to the measured trajectory, I used the metric between the two distinct curves, which I use these Fourier coefficients of the closed curve, because a closed curve is a 2 pi periodic function on the polar coordinates. So I measured the distance between these two curves, which I have used as a loss function in the optimization process. And to summarize the procedure of training the model, I first create the topologically equivalent dynamic system on the normal form coordinates, which is just arbitrary coordinates. Then train this arbitrary coordinates and the measured coordinates, which is observable. Then train the another part of the normal form, which is responsible for the speed of the oscillation, which is this omega function here. And this is the experiment I did in the wind tunnel. This is the flutter rig, and this system oscillates at certain wind speeds, and I measured this flutter phenomena with this kind of rig and stabilized the unstable periodic solutions using this shaker with feedback control. So this is the measured bifurcation diagram. These are the measured bifurcation limit cycle oscillations, stable limit cycles in the upper branch and the unstable limit cycles in this lower branch. And we can see that the bifurcation diagram is quite accurately predicted, and also we can predict the phase trajectory of the limit cycle oscillations. And so I also trained the speed of the oscillations using the optimization, which I used loss function to minimize the mean square error using diffqflux.jl. So you can see that the speed of the oscillations are very accurately trained on the stable branch and as well as unstable branch. The trick of a little trick to train unstable branch was because of the unstable predict solutions for Hopf bifurcation is unstable direction of this periodic solution is on the reduced direction, and the radius of the amplitude of the oscillation is a fixed point. So I only did the time integration in the tangential direction, so which is a trivial which corresponds to a trivial Floquet multiplier. So I didn't have any problem with the stability issues in this case. I need to go fast, and I'll show you another example of using invariant manifold and this bifurcation theory in training for a system with mechanical system with harmonically forced systems. This type of a system has also invariant manifold, which we can understand as a nonlinear version of modal subspaces. So like these forced systems also have bifurcation diagrams, which is called frequency response functions. And if we fix this forced amplitude, then we can have one of the this frequency responses plotted here. And so this system is actually a two-parameter bifurcation problem with which like three parameters are forcing amplitude and the forcing frequency. And this red curve in the middle is called the backbone curve, which characterizes the nonlinear resonances. So this equation here is a normal form of forced mechanical system in polar coordinates. This rho is amplitude of the vibration, and this psi here is the phase difference between the force and the response. And if we measure the phase of the response and as well as the phase of the force, then we can train this normal form using the input-output map generated from this equation here. And in this case, the steady state responses have very nice input-output map relations. In this case, rather than using numerical integration in training the machine learned model, I used kernel-rich regression with which I used kernel functions.jl and optim.jl to optimize the hyperparameters here. So from the bifurcation diagram, I have trained this machine learned model to predict the steady state response of the system with the invariant manifold. And this is the experimental example here, which is just called nonlinear electromagnetic system. And I excited the base structure here using the shaker. Oh no, I didn't excite it. My colleague excited this, and I used data of this this experiment to build a model, and this is these curves are bifurcation diagram with fixing forcing frequency and varying forcing amplitude. These curves are called S curves here, and these blue dots here are used to train the model. No, green dots here. These green dots here are the training data sets, and using the normal form model, I trained the machine learning model, and you can see here that these blue circles here are the untrained measurements, and you can see that the model can predict the untrained bifurcation diagrams quite accurately. And from the backbone curve here, measured backbone curve here, we can see that the machine learning model can extrapolate as well as the interpolate here. I used Julia SciML packages to build a parameter-dependent OD models from data, and machine learning modeling approach developed here uses invariant manifold and bifurcation structure as domain knowledge. And for the future work, I'm trying to identify invariant manifold from delay embedding maps and discover. Here, I only discovered the tangential dynamics of the invariant manifold, but I want to discover the transverse dynamics of the invariant manifold, which I can build a much general dynamical system model.
All right.
Thank you very much. Yeah,
right.
all.
Sorry, I had to cut you off this point. It's a great talk. I really enjoyed looking at all the experiments that you generated data from. But we do have to move on to the last item of the day, and I'll have to give a few announcements. So I want to thank the speaker once again, and then make a few announcements. Thanks, Kyoung.
Yeah, thank you.